In this section, we're going to look at single slit diffraction. Basically, we're going to see what happens when a plane wave meets an obstruction with an opening where the light can diffract. This will produce a pattern that we call a diffraction pattern. Now, if you remember, Huygens' principle stated that any point on a wave can be a source of new wavelets which constructively interfere to produce the next wave. So for instance, if I have a plane wave propagating from left to right here, each plane wave is going to produce a new wave in front of it as it propagates forward. With Huygens' principle, once we come to an obstruction, the light is now going to only have a few different points from which it can propagate. So in this case, we're going to keep this simple. Although the slit has a finite width, we're going to use a single point here to represent the opening where new waves are going to be produced. And clearly you can see here, if we only have this point or only have a few points here, we're going to get these curved wave fronts, and the light is going to spread out from that particular opening right here. Now, if we just use geometrical optics, where we had rays to represent the propagation of the light, we would get pretty much a point about the size of this opening right here. But clearly we can see that the light is going to diffract out in all directions from that point. Now, if I represent the opening with more than one point, we can see that the light from more than one point can interfere with itself. In this particular case, we see two sets of waves being produced. The blue set of waves is being produced by the upper point. The red set of waves is being produced by the lower point. And sometimes they constructively interfere, sometimes they destructively interfere. It depends on the geometry of the wave. At an angle of 0, basically the red and the blue waves overlap. The wave fronts are the same. They are in phase. So we'd get constructive interference. At other angles, they have different wave fronts at different positions. And therefore, we'll have some degree of constructive to destructive interference. So again, if we look at the directions where constructive interference takes place, we see that there's constructive interference at an angle of 0, and then there's constructive interference at a positive angle and a negative angle. And again, this is oversimplifying what the single slit is. Here we're only representing it with 2 points, where in fact it actually should be represented by a continuous set of points. Destructive interference happens when the blue wave and the red wave are 1/2 wavelength out of phase, or 180 degrees out of phase. And in these directions, we would get destructive interference where no light would appear. So this is what the diffraction pattern actually looks like. Again, you see a strong central peak. This is due to going forward in this direction where we have constructive interference. So we get a pretty wide, bright central feature. And then these dark lines represent where the destructive interference takes place. Now, in this particular case, we only showed one line of destructive interference. We had a very small opening here. So because the opening was really pretty close to the wavelength of light, we had a very broad diffraction pattern. With smaller apertures, we can see more bright and dark lines occurring at different angles. So again, the result of a single slit diffraction, or a single slit, I should say, opening, is this diffraction pattern right here. Here we've restricted a laser beam in the X direction, but we haven't restricted it in the Y direction. And notice how it diffracts out in the X direction, but the original beam was approximately the width that we see right here. So there's no diffraction that takes place in the Y direction because there's no restriction. So the tighter I make this opening, the more narrow I make this slit, the more spread out this pattern is going to become. So here we have a wider slit. Here we have a narrower slit, and we notice two things. With a wider slit, it's brighter, and the features are closer together. With the narrow slit, we're blocking more of the light, so the pattern is less intense, but it also spreads out more. Again, we can see why this happens. Here's our narrow slit, here's our wide slit. In our narrow slit, the central peak happens at 0 degrees. And again, the two bright peaks that flank it are off in these two directions here. However, if I move these points apart, which would be representing a larger aperture, a larger slit here, notice that my directions of constructive interference are closer together, and we get this bright central peak. In fact, if I took this opening to infinity, where it was an infinitely wide opening, we would only have a bright central peak, and that would basically be a plane wave which would have propagated from left to right without any obstruction. We call this type of diffraction Fraunhofer diffraction. When we have a plane wave incident on some aperture, some opening, a slit, it can be a circular opening, it can be some other shaped opening. As long as the waves are coming in as plane waves, as they pass through here, the type of diffraction pattern we get is this Fraunhofer diffraction. Again, our brightest feature of this is at the center. And as we go away from the center, the intensity of these peaks become less and less. Now, again, we can look at the different conditions we have for constructive and destructive interference. Before, we just took two overlapping patterns and saw where the wavefronts were in phase and where the wavefronts were out of phase. But again, think about this opening with a width of A, where A is much, much less than the D, which is the distance from our opening to the screen. So this is not proportional right here. Here, A would be, not approaching the wavelength of light, but not all that large, perhaps a few millimeters, probably even smaller than a millimeter. D would probably represent a few meters if this were a laser beam. And here we can see that if I take the center of this slit and I take the edge of the slit, which has a distance between it of A over 2, even though in this drawing clearly D2 is longer than D1, if A is much, much less than D, essentially the difference in path is nearly 0. Okay, again, A, we think about in millimeters, big D, we think in meters, even though they look like they're two different distances here, effectively, they're the same distance at the center. We get constructive interference. If I go off at an angle, I can see that this distance, D1, even if A is much smaller than D, is going to be greater than D2. And the path difference between these two, if it's 1/2 wavelength, it'll put them 180 degrees out of phase, and we will get a dark destructive interference fringe right there. Now, again, looking at the path length difference between the two. Basically, if we take A over 2 as half the width of the slit, we take theta as being the angle on this right triangle, but also the angle with respect to the normal to the slit. Okay? The path difference, okay, is the opposite side on this right triangle, which is A over 2, the length of the hypotenuse, times the sine of theta. So for the conditions of destructive interference, all right, we want basically that the wavelength divided by 2, the path length difference, we want it to be equal to A over 2 times sine theta. I can multiply both sides by 2. I get that lambda is equal to A sine theta. Lambda is a wavelength. A is the slit width. Sine theta is the sine of the angle that it makes. We get the condition where sine theta is equal to lambda over A. We're going to get a dark fringe. In fact, if we think about this path length difference, okay, if it's equal to lambda over 2, or lambda times 1 plus 1/2, or lambda times 2 plus 1/2, we're going to get a dark fringe. We're going to get destructive interference because the two waves are going to be out of phase. Now, again, really to treat this properly, I would have to treat this as a string of infinitesimally small sections right here, an infinite number of points between each side and looked at the phase relationship between all of them and then added them up. But in this case, I'm pretty much just treating them as two separate points and seeing which conditions give me constructive interference and which conditions give me destructive interference. So again, looking at this, the sine of the angle of the dark fringes is going to be equal to m lambda over a. Remember, for the first fringes, sine theta was equal to lambda over a. So in this particular case, if I just add some integer, if I just multiply by some integer m, okay, I will get destructive interference. Here, the two waves are off by half a wavelength. Here, they're off by 1.5 wavelengths. Here, they're off by 2.5 wavelengths, so on and so forth. So once again, we can see here where our different dark fringes are going to occur. And notice that there's no m equals 0. That would correspond to the center of this, which is clearly a bright peak. So again, in general, destructive interference occurs for a single slit of width a when sine theta is equal to m lambda over a. M is some non-zero integer. Doesn't give any information about the variations of intensity along the screen, but it tells you where your dark fringes are.